All right, hopefully everybody can hear me. We will start here in just a second. Looks like people are joining. That's good. Okay, let's go ahead and start. Welcome to the 5th live lecture for the POSA Communications MOOC. This is the 3rd week of the class, and in this week we'll be wrapping up discussions of bound services, focusing on the use of bound services with AIDL and the binder framework. And then we'll also begin the 3rd programming assignment. We'll cover my solution to the 2nd programming assignment later in the week. And another set of things that will start this week will be a set of lecture videos that are pre-recorded that cover the remote inter-process communication mechanisms available on Android that you can use to talk from an Android device to a server located somewhere in the cloud. And so there's a bunch of videos that you can watch. Those will not be presented live, but the format of the videos are very cool. And my colleague, Professor White, has recorded the videos that talk about remote inter-process communication and HTTP programming and retrofit and things like that. So that'll start this week too. The videos are already uploaded, and that will continue into the next week, where you'll also be doing using some of the knowledge of how to use the remote inter-process communication mechanisms in Android together with bound services and local inter-process communication mechanisms to write an interesting programming assignment pretty much from scratch. We'll give you some videos that talk about the various features, but you'll be doing the bulk of the coding from scratch. Okay, so what we're going to do today is we will first start by talking about local inter-process communication. Let me go ahead and share my slides. All right, so make this visible. There we go. So what we're going to start with today is a discussion about the Android interface definition language and the use of the AIDL, as it's called, together with the binder framework. And we'll be talking about how AIDL and the binder can be applied, and we'll be using a bound download application as a running example. I'll provide you with links to this shortly, so you can download the application. We'll also go through it today, and we'll show how to use AIDL and the binder framework so that activities can interact with bound services both synchronously, in other words, blocking, as well as asynchronously, in other words, through callbacks. As you'll see as we go through this discussion, AIDL and binder support statically typed, object-oriented remote method call programming model via the proxy and broker patterns. So you'll get a chance to see these patterns applied, and then we'll talk later in probably next week about those patterns in more detail. So let's start by motivating why we need AIDL and the binder. What problem is it solving? Well, as you've no doubt noticed by now, there's a number of situations where you may want your service to run in a different process than the client components. So you might have activities or other services, and you want one other service, or at least one other service, perhaps more than one service, to run in a different process because you want to share it, you want to isolate it from the point of view of failures and hangs and so on. You maybe want to make garbage collection have less of an impact because not everything will be garbage collected simultaneously, et cetera, et cetera. So there's a bunch of reasons why you might want to split things up. And we talked about a bunch of these examples before. Of course, an object in one process on Android, and this really is true in general, cannot normally access objects in the address space of another process. So in order to be able to communicate, you've got to find some way of dealing with this. Now, this is intentional. The programming model in modern operating systems, Linux, of course, or Android Linux being examples of that, but it's also true with other versions of Unix. It's true with versions of Windows and Windows NT, et cetera, et cetera. Processes are designed to protect their contents from accidental or malicious access by other processes. You can read more about what a process is here. So what you need, if you want to be able to communicate, is some way to bridge together between the code in one process and the code in another process. And this, of course, is called inter-process communication, or IPC. And that's what we'll be talking about. Now, keep in mind, we've already talked some about this, but we're going to go in further detail and give you a different flavor of IPC. If you have an activity that wants to perform IPC with service objects that reside in other processes, there's some additional things that have to be done. And you've already got a flavor of that with the earlier discussions that we had about passing messages back and forth, but we're going to talk more generally about this. So part of what has to go on if you want to send information between address spaces is the objects that you work with, the Java objects or C or C++ objects, whatever kind of objects they are, they have to be transformed somehow into bundles or parcels that Android understands. And so that what happens here, the images are supposed to show objects, which are sort of your Lego pieces that may have different shapes and sizes and colors and so on, defining different methods and state and so forth. And these things get converted into lower level mechanisms, basically bundles, parcels, messages, et cetera, et cetera. And you can read here for more information about bundles and parcels. Parcels are the low-level mechanisms that are used to pass the data back and forth, and bundles are basically a mapping of strings to parcels, and that's what is used with messages, as we've seen. And once you've converted the objects into the native objects or the Java objects or C or C++ objects, whatever kind of objects you're working with, once you've turned those things into bundles and parcels, et cetera, then these bundles and parcels can be exchanged via the optimized Android Linux binder framework. There's lots more information here on the binder. And that's actually used to shove the data back and forth across the backplane, across the operating system on a single device. And at the heart of all this stuff, of course, are marshalling and demarshalling mechanisms. That's the secret sauce that does all this stuff to move information back and forth. You can read more about marshalling and demarshalling here, and we'll also talk a bit about it. If you have any questions, please feel free to let me know. Marshalling converts data from a native format, which is in Java typically, but it could be C or C++ or other languages that are supported natively on Android, into a so-called linearized format. This is the marshalling process. So you take the objects and you turn them into basically these parcels or byte structures, and then those things are sent to the other side, and they are demarshaled or converted from the linearized format back into the native format. So if they were originally in Java, then you can put them into a parcel, and then the parcels can be sent across to the receiver side where they're turned back into the Java objects. Now, the other cool thing about this, by the way, is that you can actually have C and C++ talk to Java by simply following the same rules for converting things into this so-called linearized format. The particular example we're going to talk about is going to be the bound download application, and it's very simple. It just passes strings back and forth. You'll see that there's some variations on this as we talk more about it, but basically that's the business logic that's being passed back. But AIDL and binder, as we'll talk about here shortly, support marshalling and demarshalling and passing and so on, a much wider range of data types. In fact, open-ended, because you can define your own ways of marshalling and demarshalling parcels. Now, what's the issue? Well, let's face it, if you've ever had to write this kind of code, it's extremely tedious and error-prone. Manually writing code to marshal and demarshal objects is very tedious and error prone. You have to be able to understand how to handle primitive data types, arrays of primitive data types, parsellables that can be used to encode entire classes or groups of classes. And you have to get this all working correctly, both for the sender and for the receiver side, which starts to get very daunting. So that's a process that you really would like not to have to write yourself a whole lot. Even using messages and bundles can get complicated quickly as you get more complex data types. So if you think back to the programming assignments that we've been doing, we've been sending messages back and forth, but they're fairly straightforward. They include some stuff in there. They include things like the URL that you want downloaded. They include the path name where you find the images. They include a variety of different things. The more complicated stuff they include are things like messengers and so on. But even for something like that, as you've seen, if you've been watching the skeletons unfold over the past week, there's a whole bunch of stuff you got to think about, and you've got to write all these methods that convert and deconvert between messages and bundles and method calls, and it just starts to get really tedious. And it's often hard to tell at a glance what the schema is, what data is actually being passed back and forth. And this gets worse and worse as you have more and more methods with more and more data. Go back and watch the programming bound services with messenger slides. You get a feeling for that. You have to write all these factory methods that do all this stuff, and it's cumbersome and tedious. Therefore, to solve this type of problem, Android provides a compiler called the AIDL compiler that automates the marshalling and demarshalling process. And you can read more about this at this link, and we're about to talk about it in more detail in just a second. So let's talk a little bit about the AIDL and the binder framework. So AIDL, which is really the language, and then there's a compiler called the AIDL compiler, that provides a way in conjunction with the binder framework, which is really the communications middleware that moves information back and forth. It allows you to be able to access objects in bound services that looks a heck of a lot like making method calls on conventional Java objects. So the abstraction you get is one that should be very, very familiar to you if you've worked with Java, which of course everybody has if they're taking an Android course. So the abstraction you see as a programmer is basically typed method invocations on remote Java objects, where remote means running in a different process on the same machine or on the same device. You can't use this mechanism to talk, say, to a web server. That's not what it's intended for, but it's intended for communication between processes on the same device. That's the programming abstraction that you see. Under the hood, there's layers of middleware that take care of all this stuff. We'll talk more about these layers in just a minute. Down in the operating system, there's a binder driver, which is a high-performance device driver in the Linux kernel that's optimized for communication between processes on Android devices. And then something else that's provided by the AIDL and the binder framework is an interesting concurrency model based on thread pools that are managed internally by the binder framework. So a lot of stuff that we had to do ourselves with thread pools now kind of comes along for free, as long as you're careful in how you scale things up. Now, what is AIDL? Well, AIDL is basically a superset of a subset of Java, which of course means it could be anything, but it's basically a subset of Java. Doesn't have all Java interfaces defined, all the mechanisms in Java interfaces, especially the Java 8 interfaces, but it defines a subset of Java 8 interfaces, and then it defines a few additional keywords like one way and in and out and so on to indicate the direction in which the parameters are passed. This is a very simple AIDL source file called download.aidl, and this defines a method called downloadImage, which takes a string, which is the URL, and it returns a string, which is the path name to where the image was downloaded. Now, of course, you could add more parameters to this. This is a very simple example. A real example might do more stuff than this. And it's also just using strings, but a real examples can use more than strings, as we'll see later as well. Each of these AIDL interfaces is defined in an AIDL file, or a file with a .aidl suffix, and it's saved in your source directory. So here's the source directory for the bound download application, which we'll look at later. As you can see here, we have the source directory, the Vandy MOOC, and inside of here we've got 3 files: download call, download callback, and download request. And I'll explain how these things work when we look at the example. The AIDL compiler, if you put an AIDL file, a file with an AIDL suffix in the source directory, the AIDL compiler is automatically called for this file. And what it does is it generates the corresponding Java interfaces and classes and sticks those things into the gen directory. So it's going to generate some code for all these things. And there'll be 2 classes that'll go in there for each of these things. It's kind of nested inside of the file, but there's a couple of classes. One is something that's called a stub, and a stub is handled on the service or server side, and this extends the Android iBinder mechanism, and this is used to basically connect the generated code that comes out of the compiler with the implementation of the AIDL interface. That's where your code goes. So that would be the implementation of the download image method, for example. And then there's also a proxy that inherits the Java version of the AIDL interface, and this is used to shield the clients from the inter-process communication details. So as a client, you simply call a method on the proxy, and that then works in conjunction with the binder to send the data over to the service side, where a stub is used to turn around and dispatch an upcall onto the implementation of the interface's methods. In this case, there's just one method, but there could be multiple methods. So that's pretty much all there is to it. The binder under the hood optimizes the communication for cross-process calls. It's got all kinds of clever tricks it does to make things run fast. It also works properly if you have co-located calls. So if you end up co-locating things in the same address space as opposed to different address spaces, there's optimizations there that make it work very efficiently. You can find out more about the iBinder stuff here. And as a result of using AIDL, the applications rarely, if ever, access the underlying binder directly, but instead they use the generated stubs and proxies. It's possible to get to the underlying binder, but you really wouldn't want to do it for the most part. Okay, so that's a quick overview of AIDL and binder. Let's take a break, and I will go and answer some questions. All right, let's see. Start off with a few questions here. What are the roles of intent service from command processor in our assignment 1? Who is the creator, et cetera, et cetera? We're going to talk about this when we get to the command processor pattern description. And if you're impatient, you can go ahead and watch the video, which I think is in either next week or the following week. It's probably in week 5 is my guess, but it's definitely uploaded to the website. Let me go ahead and find it. I'll show it to you so you'll believe me. Let's go find the website. Share the website. Here's the website. Here are the lecture videos. And if you take a look at the command processor pattern, the command processor pattern videos basically show a mapping of the command processor pattern onto the intent service. So go and take a look at that. While I'm here in my website, let's go ahead and take a look at a couple other things real quick. Here's the course syllabus. And as you can see, we've gotten through the bulk of the material on Android started services. We talked about the intent service. Last week, we finished up bound service with messengers. And now we're basically talking about AIDL, and we're about to talk about programming bound services with AIDL. So these are some of the things we're about to talk about. And then what's going to happen here after today, the rest of this week, in addition to watching these videos, if you're curious, you can also start learning about remote inter-process communication. And as you'll see, if you take a look here, for week number 3, we'll be uploading the videos about AIDL as part of week number 3, but then there are also about 7 or other relatively short videos. No video is longer than 8 minutes and 45 seconds. Most of them are about half that time, that talk about HTTP programming, cloud services, requests, responses, and so on for HTTP. So that'll give you an overview of some of the inter-process communication mechanisms. You should watch these videos. We're not going to be presenting these videos live. They're recorded in a very interesting way using a light board, so it almost looks like it's live, but they're pre-recorded. And then week number 4 will mostly focus on this material related to inter-process communication that goes across from an Android device to a cloud service, and it'll talk about things like making method invocations using RESTful messaging. It'll talk about JSON for encoding the data. It'll talk about retrofit, which is a really cool way of doing remote procedure call like mechanisms using code that looks almost as cool as making AIDL calls, and so on and so forth. And that'll help prepare you for the final programming assignment, which we'll be releasing later this week. And then here in week 5, I just put all the videos related to patterns. We might cover 1 or 2 of these next week just because it's fun to do some live lecture stuff. But the bulk of the lectures from here on out that you'll be doing as part of the assignments will be pre-recorded, and they'll cover the inter-process communication mechanisms. So I just wanted to cover that so that people would have an idea of kind of where things are coming. Someone wants to know, what's the problem being solved by AIDL? Well, if you go back and watch the video, it explained what the problem was being solved by AIDL. AIDL allows you to invoke method calls. They look pretty much like regular Java method calls, except the implementations of the methods reside in another address space. They can reside in another process, except the way that you interact with them is by making method calls. So it's a much cleaner and more convenient programming model than having to try to manage the messaging manually. That was really what we just talked about. So go back and watch those videos if you have any questions about that. Let's see. Is there any tools in Eclipse or Android that can make the binder framework visible and allow you to debug it? When you say binder framework, I'm not quite sure what you mean. Do you mean the lib binder mechanisms that are written in, that are part of the libraries that are linked against your application? In which case, you should be able to just sort of step into that code if you've got the Android source code compiled in debug mode, so you have access to that. You may also mean the binder driver, which is the mechanism that's implemented in C and C++ that lives down in the OS kernel. That you'd have to use some kind of kernel debugging mechanisms. But you should be able to set up the source code for the other parts of the binder, so you can step through it with the debugger. Or you could also turn on logging and watch the log tracing information. There's actually a number of places you can go on the web that give you very, very detailed walkthroughs of how the binder works. I give some links to those places in the video we just looked at, so I recommend you take a look at that. There's some really good presentations that go into a great deal of depth for this whole thing. Question about assignments and quizzes. There will be 3 assignments. That's correct. The 3rd one will come out later this week. So the first 2 assignments are already released. Hopefully you're well on the way to completing the first one, which is due in a couple days. Note that we will have the virtual office hours this week on Thursday, not Wednesday, so that I can go over my solution to assignment number 1 after you've turned them in. And we will probably have 4 quizzes, is my guess. We'll have a quiz this week and a quiz next week that'll cover. Quiz this week will cover bound services with AIDL, and it'll cover the first part of the inter-process communication mechanisms for networking and remote inter-process communication. And then next week we'll cover pretty much entirely the material on remote inter-process communication. We don't have any quizzes for the pattern stuff. Let's see. Is it possible to use socket message queue for IPC in Android? Sure. You're welcome to use sockets. I think you'd be kind of out of your mind to do sockets, but you're certainly welcome to use them. They're available as part of the API, and so you can program against them if you want, but there's almost always better mechanisms to use in Android rather than using sockets. Okay, so I think that ends the first round of questions. If there's more questions, please don't hesitate to bring them up. Let's now go ahead and go back to the video for a second. I guess I'd better bring up the slides. All right, we're almost there. Okay. What I'm going to do now is give you an overview of the bound download application to give you a new perspective or another perspective on how to program bound services using AIDL. So this particular application uses AIDL and the binder mechanisms to interact with bound services to download and display images both synchronously and asynchronously. It follows along with our common model of having silly pictures of me from many years ago that you can download and marvel at my transformation over time as my hair got shorter and shorter. You'll see that we have one activity, that's the download activity, and then we have a pair of bound services. One downloads things synchronously, one downloads things asynchronously. And of course, under the hood, they use sockets using the URL class in order to be able to send out a GET request to download content at a particular URL. So nothing too particularly new and different in that respect. It looks a heck of a lot like a lot of the other assignments we've done, but the main thing to focus on is the architecture of the solution. We'll be using AIDL and binder for the local inter-process communication between processes on the same device, whereas HTTP and of course TCP is used for remote inter-process communication with the web server or web servers, depending on what links you give it. Here's a basic overview of the classes that are involved in this. We see there's a relatively small number of classes. We have a download activity, which is all the UI related stuff. It inherits from download base, which is really literally where all the UI stuff resides. Download activity basically inherits from download base, and then it provides a bunch of methods for interacting with the service and getting the results back. We have a download bound service sync and a download bound service async, and those are the two services that we're going to have, and you'll see why we have two of them in a minute. And then we have download utils, which is just a typical place of sticking a bunch of files that we'd like to reuse, or a bunch of methods that we'd like to reuse for various purposes. And here you go. You can download this application here in the examples directory from the POSA 15 website. So I finally found something to put into the examples directory that had not already been in a directory from a previous class. So what we're going to do now is we will go ahead and look at the solution, and then I'll come back and we'll summarize all this stuff. So let's go over here, and we will make my editor display on the screen. All right, let's get this thing in proper focus. There we go. Okay, so here's the basic file structure for the project. We have a manifest file, which, as you can see, has one activity, the download activity, and then we have a pair of services, download bound service sync and download bound service async. I put them in separate processes. I could put them in the same process by giving it the same name. I could take them out of processes altogether just by removing this or this, but I chose to put them into their own separate processes just for fun. You don't have to do that, of course. Here then is the source code. Let's take a look. It's got the typical structure to it. Start out with download activity. There's a lot of comments in this file that explain how everything works, and there's also an explanation of the patterns that are being used to implement the various parts of all this stuff. Download activity extends download base. We'll take a look at download base in a second. That's where most of the UI related stuff goes. Download activity defines something called download call, which is essentially a reference to a download call object that resides in the service. And this is basically allows two-way synchronous calls. So you can invoke a method and then wait for it to return. Here is download request. And download request, as you'll see, is going to be it's a reference to a one-way call, and that's used to talk to the async service, and it passes over the URL to download, and it also gives a callback object, and we'll look at the callback object later. So that's a way of splitting invocation from response. We then define the service connection object for the sync service, and as you can see here, it is an instance of service connection. You can see there a service connection, and it's on service connected method. When it's called back, it uses the generated stub to convert the I binder that comes back from the service into essentially a proxy that we can use later to invoke an operation that will result in a two-way method call, and you'll see how that works. You can think of this as essentially a factory method that's generated automatically by the AIDL compiler, and it stores that into a reference. We disconnect if the server crashes and is no longer available. Here's the async version of this stuff. It's very similar. The only difference really is that we have a download request instead of a download call. Up here we had download call, and then down here we have a download request, but it's the same basic idea. We convert the I binder into a proxy that's stored in mDownload request, and you'll see how that gets used in a minute. And then on service disconnected just sets that back to null. Okay, so that's how we get the data. That's how we are going to get connected to the binder objects that reside in the sync and async service, respectively. So that's where those things come from. Now, the other thing we have to do is we have to find a way to get the results back when everything's done. And in order to do that, we're going to implement something that's called a stub. Now, this is only used for the async version. So this is used when you need to get an asynchronous call to come back from the async service back into the download activity. And to do this, we're going to create a download callback stub, and I'll show you what all these various methods and classes are later. And download callback stub is used to implement a return method called sendPath. And so sendPath, when it's invoked, will be called back from the service, and it'll take the path name to the image that was downloaded. It'll create a new runnable that will display that bitmap, and then it'll go ahead and run that thing on the user interface thread. It'll run that runnable on the user interface thread. And the reason it runs it on the user interface thread is because stubs get run in a background thread. A stub gets run in the background thread that's created automatically by the underlying binder framework. And I'll talk a bit more about that when we get a little further along. So this is how we get results back. All right, so that's kind of communication portion. Here is the run service method. This is what gets called when someone clicks on a button to either run synchronously or run asynchronously. We get the URL, we hide the keyboard, we switch to see what button was pressed. Is it the bound sync button or the bound async button? Could be either one. The easy case is the bound sync method. And what we do in this case is we go ahead and we invoke a two-way call on the mDownload call reference. This is a reference, this is a proxy to the implementation that lives over in the service. And we invoke download image, passing in the URI. And this call will block until download image completes and sends its result back. It'll block the main thread of control. Now, in real life, you probably don't want to do this. I'm just doing it here to illustrate how to do it. And I'm going to show you a little sleazy trick you can play if you are so inclined to do devious things. But this is going to block the main thread of control till it's done, and then it will display the bitmap. If you don't want to block the main thread of control, of course, you could spawn a thread or use an async task. There's any number of ways to avoid having to block. So that's what we do if we're doing a synchronous call. Conversely, if we're doing an asynchronous call, then we split up our code into two parts. The first part is to make a one-way call to the download image method, passing in the URI, and a callback object that will receive the result via the send path method we just looked at up here. So this is a one-way call. It goes ahead and transfers the URI and the callback object reference over to the async service, and it returns right away. This call will not block the main thread of control. All right. Here's the onStart hook method. This gets called back when the activity is about to become visible, and that's where we do the binding. To bind the service, we bind to the async service, we bind to the sync service. You can see I use my little factory method pattern mechanism here to keep the code real simple and clean. Here's onStop. It basically does the same thing, except it's called unbind service. There's a bunch of helper methods here, like get download call, get download request, get download callback, which we can use for various things, especially for things like testing. We don't really use it much except for the testing, which I don't include here, but we have some test cases we've written for this code too. So that's basically download activity. Here's download base. Download base extends activity, and it defines all the UI widgets and components, like the text that's going to be used to prompt the user, the image view where the result will be stored, bitmaps we're going to use, the current bitmap and the default bitmap for resetting the image. There's a method here for hiding the keyboard, displaying the bitmap, getting a string, resetting the image. Here's the onCreate method. This is what gets called back when the activity is about to start. We load the content view, store a bunch of the various views, and then here's the little sleazy trick I was telling you about before. We turn off strict mode. And basically what this is doing is it's going to allow us to be able to make blocking networking calls from the UI thread. Now, again, I put this here just to show you how to do it. There's rare circumstances where it's a good idea. It's rarely, if ever, a good idea, though. So I'm just showing you here this, and I have all kinds of comments everywhere saying, never, never do this unless you know what you're doing. I just wanted to do it to illustrate that it is possible to do so. And this means that you won't get an exception when a blocking call is made in the UI thread. Okay, so that's basically the activity. Let's take a look at the AIDL files now. So there are three AIDL files. Probably should have shown these first, actually. So this is the AIDL file that's used to synchronously download an image. This will block the caller, block the activity while the call takes place, and it's passed a URI as the input, and it gives back a string. Actually, we could give back a URI for that matter. It's either one is perfectly fine. Strings and URIs, in my mind, are largely interchangeable. It's kind of annoying that they have two of these things, but that's the way it works. So download image is basically going to result in a two-way blocking call. So you better be prepared for it somehow, as we showed in the code that turned off strict mode. Here are the asynchronous versions. Here's download request. Download request has a download image method, but it's defined as a one-way method. And that means that it's not going to block the caller waiting for the result to come back. It just sends the request over and returns right away. Assuming the code is running in the other process, by the way. If the code is co-located, then download image will actually block until the call is completed in the single process. In order to be able to get the results back, we have to pass in a callback object, which is defined of type download callback. And if you go here and look at download callback, you'll see that download callback defines a one-way method called send path, and that's used to send the result back to the download activity. So that'll be sent from the download service async version back to the send path method defined on the stub in the download activity. Okay, now keep in mind that when you define these AIDL interfaces, that if things run in separate processes, they're processed in a pool of threads. Let's now go take a look over here at the implementations. We'll start with the sync implementation first. This is download bound service sync. And once again, it's heavily commented, explains what it does, talks about patterns it implements, and so on and so forth. Download bound service sync extends service. Now, the thing to note about this code, by the way, it's really, really short. So it's very cool. This is the big win about using AIDL. Previously, someone had asked, what problem is AIDL solving? Well, the problem that AIDL is solving is having to write all this gobbledygook code for managing the transfer of data between sender and receiver. All that stuff gets sucked up into the AIDL generated stubs and proxies. So here we have download call impl, which is an implementation of download call stub. Remember, stub is the code that's generated by the AIDL compiler that's used to connect or glue together the generated code with the code you write to implement the method defined in the interface, or the methods defined in the interface. Here is the download image method. You can see download image takes the URI and returns a string, and it basically calls download utils download file. I could say download image for that matter, it doesn't really matter. And that goes ahead and downloads the URI and returns it. So this is a blocking two-way call. However, this method runs in a separate thread of control. The binder framework spawns a pool of threads, I think up to perhaps 16 threads in the pool. And those threads are available to process requests that come in to the service. So this call will block in a background thread that you did not have to spawn. That's handled for you. Here's the onBind method. It simply returns the download call impl, this guy right here, which is a stub, which of course implements iBinder. And then down here is simply the factory method make intent, which makes us an explicit intent for being able to have the bind service resolved to the right place. So that's all there is. That's the implementation. You can see that most of this code is just boilerplate code that you might even put in a library or auto-generate. And the only thing that's even remotely interesting and application specific is the download image method itself, indicating that it goes ahead and downloads the file and will block until the file is downloaded. So that's the download bound service sync. Now go take a look at download bound service async, which is slightly more complicated, but not that much different. In fact, it's almost identical in terms of the code. It just splits things up a bit more. Download bound service async is a service. It defines a download request stub implementation. And you can see what this does. This is actually pretty cool. Check this out. What it does is it goes ahead and it takes the URI that was passed in, as well as the download callback reference, which resides back on the activity. It calls download file to download the file image, and then it takes the result of download file and it sends that path back to the client activity via a callback. So you can see this code looks almost identical to the code that's here. Notice how they're almost the same. This one simply calls download file and just returns it directly because it returns a string. In this case, download image is void. It doesn't have a return code because it's a one-way method. And so we go ahead and download the file, and then we send the image back to the client via the callback that was passed in. Now, this particular example has the same thread that downloads the file be the one to return the result. You don't have to do that. You could actually queue up the request and the callback object in some other queue, handle that in some other thread, and then send the result back from that other thread. So this gives you a lot more flexibility in terms of whether or not you block. Come down here, you can see onBind is identical, make intent is identical. So everything is pretty much identical except that download image has two parts to it. We download the file first, and then we go ahead and send the path back. And that's basically it. There's a download utils file, which is more or less the same thing we had before. In the other examples, it makes a temp file and copies the image into the file, blah, blah, blah. Nothing real surprising there, so I won't spend much time going through it. You're welcome to take a look at it at your leisure. Okay, so that's basically the implementation. Let's now go and finish up. Hold on a second. Let me go ahead and I'll finish up the summary, and then I'll take questions. Okay, so let's go ahead and summarize. Let's go ahead and summarize this particular presentation. The Android interface definition language gives you a way of defining binder-based interfaces to bound services. It implements the broker pattern and therefore shields applications and application developers from tedious and error-prone details of inter-process communication. That's the real problem that AIDL and binder together is solving. You have a lot less work to do because all the stuff related to marshalling and demarshalling is pushed into the generated proxy and stub, and therefore all the things that are used to parcel stuff up and send back and forth and use transact and on-transact, all this stuff that the binder does is all hidden from you. So you can look at the broker pattern here. We'll talk more about it later. Broker basically connects clients with objects residing in a different address space and mediates method invocations from these clients to these objects. So it gives you what appears to be a method-oriented interface, but under the hood, of course, the generated proxy and stub are marshalling and demarshalling the native code into lower level format that you can pass around. There's a whole pile of other patterns that are used to implement AIDL and binder. Proxy, of course, that gets used. Activator gets used. We'll talk more about these patterns later. There's other gang of four patterns lurking in the implementation that we might get a chance to talk about if we have time. So if you watch the videos in the upcoming section on the communication patterns in Android, which is in section 5, I believe, or week 5, you'll find the information there. AIDL and binder are used very, very, very frequently throughout Android. Hundreds, literally hundreds of places they're used. They're used in the core framework. They're used in the packaged applications for all kinds of stuff. It's a very, very widely used mechanism. And the reason is because it gets rid of a lot of the accidental complexities of trying to manage the memory directly. And of course, I should also point out that this is basically the same sort of capability you would get with Java remote method invocation, Corba, DCOM, retrofit. It just kind of highly optimized for Android communication. Now, we've only scratched the surface of this stuff. And if you really want to get a much deeper discussion about AIDL and the language, how the binder mechanisms work under the hood, go ahead and watch some of the supplemental videos that I've uploaded for this week, which come from some lectures I gave a number of years ago that go into way, way, way more detail on how things work. So you're welcome to take a look at that stuff if you want more information about how Android works. But I didn't want to spend too much time on it unless you're really curious, because it's very, very detailed. Okay, let's go ahead and do some questions. So AIDL hides the complexity of managing messengers and handlers. Yes. Is it better to always use AIDL? What are the negative aspects of AIDL? Well, these things are actually discussed back in some of the early material that we covered in some of the earlier sections, and it's also covered in some of the other lectures that you can read or you can watch in the supplemental sessions. So let me just give you a quick summary here, and then you can go back and learn more about it by watching the material that's available on the website. So messengers and handlers work pretty well for very simple things. If you're just passing over, say, a string or something like we did here, a messenger handler approach is arguably about as easy You don't have to understand AIDL. You don't have to understand the generated stubs and proxies, and there may be less mechanism in the way once you understand the patterns of programming with messengers and handlers, of course. And if you use that cool little framework that I developed, that I gave out as part of the skeletons for assignment 1 and 2, where we have the on service result hook and we got the service result interface and so on and so forth, you can really make things pretty clean from the point of view of using messengers and handlers. But you do have to figure out how to encode the messages, and you'll end up writing code not unlike the reply message and request message helper classes that we added to assignment number 2. So there'll be a bunch of code you'll have to write, and the logic of the messages that are passed back and forth may not entirely be clear. You have to document things very heavily. It relies on convention. It relies on people following the rules, and so on and so forth. But it's not too complicated. In contrast, if you're building a service that has dozens of methods with very complicated data types, then doing all of that through messengers and handlers quickly gets out of control, because you end up having to keep track of all these types. If you make any changes, a lot of code could break without you really understanding how or why that happened. You have versioning issues and so on and so forth. So in general, the more complicated the mechanisms you're trying to implement, the more likely you're going to be to want to use AIDL, because it scales up a lot better. Now, the thing to remember about AIDL is it doesn't just give you a way of generating proxies and stubs automatically, which is good, by the way, but it doesn't just do that. It also gives you predefined pools of threads to run requests concurrently. So that's actually another potential benefit if you know what you're doing and you're able to write thread-safe code and use threads properly. So those things kind of come along with no extra charge for using AIDL. One of the tricky things about using AIDL, however, is you can't use a naive approach. Well, you shouldn't use a naive approach where you use nothing but a bunch of blocking two-way calls, unless you really want to have all of your invocations handled via async tasks on the activity side. The sleazy trick that I showed you by turning off strict mode for the threading policy was just for illustration purposes. You shouldn't do that in production code unless you really, really know what you're doing. So instead, you would have to put lots of async task calls to invoke the two-way methods in an async task and then get the results back. So that's one way you can do it. Another way to do it is what I showed you, where you basically split the AIDL interface into a pair of interfaces, each of which have one-way calls to send from the activity to the service one way without blocking, passing along a reference to a callback handler that also has an AIDL interface, and then having the service call back on that callback handler after it's done processing. So if you're comfortable with that kind of processing model, which is basically the ProActor style programming model, then AIDL works very nicely. That model, by the way, is actually very, very similar to the kinds of microservice patterns that use the ProActor that we were showing in at the end of the programming assignments 3 in the previous MOOC, the POSA concurrency MOOC. Same basic kind of patterns that they're applying. We're just using AIDL to do a lot of the heavy lifting under the hood. So that's some of the trade-offs between AIDL and handlers and messengers, and there's more discussion of that in the slides. Is it possible to use AIDL to pass custom types? Yes, absolutely. And in fact, for your programming assignment 3, you're probably advised to do that. And I will show you an example on Thursday that illustrates how this works. There's an example that's in the POSA 14 examples directory on my GitHub account called acronym application. And the acronym application, I believe, shows how to send parcelable objects through AIDL. And it's really cool. And you can use that to pass sort of arbitrary things back and forth. So yes, you can do that. You can use C++ code with AIDL. In fact, some of the Android system services are written in C++ or C, and they talk quite nicely with Java, as long as you define a common encoding format for marshaling and demarshaling the data from native C++, Java, or C into the linearized format, and then passing that across in a canonical way, and then reconstituting the native C, C++, or Java code on the receiving side. Everything works quite nicely. So that, in that sense, it's very much like, say, Corba, and it allows inter-language interoperability. There's an observation that Messenger and AIDL is similar to Hammer and async tasks. So, well, let's see. Let's kind of break this down a little bit. So, in a sense, the Hammer framework was message-oriented, and so you would send a message and you'd handle a message. And of course, the messenger mechanism is just a set of proxies over top of the Hammer framework. So there's no real surprise that messengers and the Hammer framework are like you know, salt and pepper or peanut butter and jelly or whatever. They go together very nicely. In another sense, AIDL, or rather, let's say async task, is a bit more of an object-oriented way of doing things. So you have a class, which is the async task base class. You inherit from it using the template method pattern. You fill in the implementations of the various hook methods as you see fit. And then you go ahead and invoke the method to execute the async task, and it goes ahead and runs in the background. So there's a bit more object orientation going on there, a little bit more strong typing. It's got generic parameters that are used to give the right type of type information to the async task generic type. And that is a bit like AIDL in the sense it's more object oriented. But I think the real strong comparison is between Messenger and Hammer. Those things really are meant to go together. AIDL and async task can be used together. You can use async task and AIDL in order to avoid having to do this one-way trick with two interfaces for async services we talked about, and instead use an async task with a synchronous AIDL method. And so there are some similarities, although they're not quite as coupled from a design point of view as Hammer and Messenger are. There's a question about walking through the binder framework. We'll walk through some of it. When we talk about the broker and proxy patterns, I'll show you some code snippets from the generated code that come out. And but it's very, 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 very complicated. So we're not going to go through it in gory detail, but we'll go through it enough so you can kind of understand the higher level abstractions that it provides. We'll talk about some of the Java level abstractions as opposed to, for example, the C and C++ versions in the kernel. Let's see, another question. When we start the separate process, when we start the service in separate processes, who does the fork? So this is basically, of course, handled by low-level mechanisms inside of Android. I believe that the forking that's done is probably initiated through the activity manager service, although it probably uses some very low-level systems classes that start processes and so on that are part of the Android systems API. You do not have to understand this, of course, in order to use Android, other than knowing that if you set the directive in the manifest file for the service, it'll cause a process to be created. Keep in mind, by the way, if you're running, when you run on Android Linux, it'll do a fork under the hood, but your application code doesn't have to know or care about that. So it's useful to know it exists. It's fun looking at those implementations, but you don't have to know it in order to write the applications. The download callback class is set as a stub object by the activity, and the download async service has this object as a proxy. That's actually correct, yes. So the way to think about the difference between proxy and stub, well, first let's talk about what they have in common. They're both generated by the AIDL compiler. The proxy is actually, I believe, nested inside the stub, so it's like an inner class. And the stub is used to connect the generated code on the service side, or a better way to put it, the server side, and I'll come back and explain why I said server side. Maybe the receiver side is a better term. Whoever is the receiver of an invocation on a method, whoever implements that method, the implementer side, is what is going to be extending from stub. And so when you extend from a stub, then you go ahead and override an abstract method that's defined in the stub, and you actually implement the method or methods defined in the AIDL interface. So the stub is what's used to connect the generated code with your implementation of the interface methods. That's what the stub does. The proxy, on the other hand, is used by the client side or the caller side, and it's used to invoke a method that runs elsewhere, or at least conceivably elsewhere, potentially elsewhere. It goes ahead and uses it to run that elsewhere, and that allows you, the application client developer, not to know or care where the actual implementation resides. So the stub is the implementation side. The proxy is what's used by the caller or invoker side. Now, for strictly two-way synchronous calls, it's pretty obvious where these things line up, right? So in a strictly two-way synchronous call model, like the download bound service sync, then obviously the stub, the implementer, is in the service, and the proxy, the caller or the invoker, is in the activity. That's real easy to understand. When we do the async version, however, things are different. In the async version, the activity, the client, also defines an implementation, which happens to be the download callback object, which has the send path method. And the download callback object then becomes a server or a receiver or an implementer, depends what you want to call it, for a method that's invoked by the download bound service async class. And of course, the thing that invokes that is the download image method, and that takes a proxy to the download callback object that resides back on the activity, and that a reference to that object is passed over to the service, to the async service. And after the file is downloaded, then the download image method in the service calls the send path method on the download callback proxy to deliver the result back to the implementer of the download callback proxy, which of course in this case happens to reside in the activity. So when you start doing asynchronous calls, you're kind of flipping the concept of client and server, or invoker implementer, or caller receiver, whatever you want to call these things. You're sort of flipping that on its head. So you're actually writing an activity that's both a client and a server with respect to the way that things work. So that's basically the explanation for that. When can we expect the Android classes? So take a look at the FAQ. It basically says we'll announce the schedule as we are able to determine when it will happen. It'll happen at some point. We don't have a fixed date at this point. Okay, let's see. Another question. Given the one-way command per definition, a void return type. Oh, wait. All right, I'm not quite sure what this question is asking, but I'll take a shot at it. So you'll notice that the one-way commands return void. Return void. You know, that's kind of an oxymoron, right? Returns void means there's no return, and that's because a one-way command only is used to pass data to the receiver, to the implementer, and not getting anything back in return. So by saying one way, you're also basically saying void. So any one-way command will always have the void return type. The question is, which AIDL words do I have? I guess what you're asking is, what other keywords are defined as part of AIDL? And if you watch the other supplemental videos I talked about, you'll learn more about the keywords. But there's a few other keywords in addition to what you know and love from Java. There's one way, there's in, there's out. There might be in out. I think there's also an in out, but there's certainly in and out. And those are used to define ways of passing parameters either to the caller, or from the caller to the receiver, from the receiver back to the caller. And if you watch the other videos, it goes into a lot more detail. Okay. So those were basically the questions that people asked. You're welcome to ask a few more questions if you'd like. We've got a little bit more time. I thought I would just go to the website real quick and point a few things out just because it's important to keep in mind a few dates that are coming up here soon that you probably need to be cognizant of. Okay, so here's the course website. I talked earlier about the lecture videos, so if you want to watch the pattern stuff, that'll be coming up in week 5. We might move some of that to week 4, a couple of these things perhaps, just for fun, because they're somewhat long. Week 4 lectures are already up. We're not going to be doing a lot of live lectures in week 4, other than maybe a pattern lecture or two. All these lectures are available already. You can watch them at your leisure. They'll be part of the next programming assignment, assignment number 3, which will be a mini project where you have to do most of it yourself. Here are the other videos from week 3 that you might want to watch for more information about Android, AIDL, and the binder. This video goes into a lot more explanation of what's going on under the hood if you're really curious how it all works. We'll talk about that later. That's basically the video stuff. Please note, for those of you who are doing the programming assignments, that programming assignment number 1 is due here very shortly, in 2 days, 2.5 days or so. And I will go over my solution on Thursdays, virtual office hours of this week. Programming assignment number 2, of course, has been out for a while. I think we finally settled down on the skeleton, so make sure you update everything. Also, make sure that you follow the instructions in the assignment in these steps for peer assessors. It's really important to make sure that you always download a fresh new version of the skeletons to make sure you have the latest version there. And let's see, there's lots of discussion on the discussion forums, which you're welcome to take a look at. I had given a presentation last week on Java concurrency for Java 7 and Java 8. And as soon as you can download the slides, they're available here. As soon as the videos are finished being post-produced, you're welcome to watch them if you have time and interest. I will send out the links to those things later. And I think that's basically it for those things. Oh, here's a good question. Is AIDL also usable to communicate between activities in a local service? Yes, absolutely. Whether the service is local or remote, AIDL allows you to use a common programming model, and it's the binder implementation that figures out what mechanisms to use based on where things reside. If it turns out that things are co-located in the same address space, then it provides an optimized path to invoke methods. Only if they're in a remote address space do things take place in using all the various inter-process communication mechanisms and parcels and so on and so forth. There are some subtle semantic differences between co-located and remote services. And if you watch some of the supplemental videos, it talks about that in detail. I wouldn't worry too much about it, although there's a few surprises that are lurking there if you're not careful because of the difference in semantics when you go remote to a separate process and the threads that are used to do that, and so on and so forth. Okay. Oh, here's another question. The programming assignments use thread pools with most code given us. What are some examples of unsafe thread code we should avoid when thread pools are being managed for us? Well, so whether or not you are given thread pools or not, the one and most important thing to remember when writing multi-threaded code is making sure that anything that shares common state is either run in the same thread always or is properly protected via some type of synchronization mechanism to avoid so-called race conditions. That's by far the most common mistake that people make with concurrent programs, is they don't properly lock or synchronize access to shared state or shared objects, thereby allowing different threads to modify those objects at different times. If you take a look on the website, there's some cool tools like the Sure Logic tools that are used to detect these kinds of problems. So a good habit to get into is to use these static and dynamic analysis tools. They will tell you pretty much everything you need to know about what's wrong with your concurrent code. A lot of times you can also avoid a lot of the problems of trying to worry about locking access to shared state by using various kinds of producer-consumer-like patterns, such as the stuff that we get with the Hammer framework or the Messenger Hammer framework, or other things where you pass information back and forth by passing messages, where you can store the information in the message and not have to actually access it in concurrently by multiple threads of control. So that's another technique. But it's kind of beyond the scope of what we're covering here to go through all the different issues of concurrent programming and synchronization. But 2 places you can go to find more information, I will point them out to you here. Just a second. Let's bring this back up. All right. So if you want to learn more about concurrent programming above and beyond what we've covered here, here are some good places to go to look. So this is the digital learning page on my website, source of many useful links to other video lectures and so on. I teach a class at Vanderbilt called CS 282 and CS 281, and the CS 282 course covers a lot of things related to concurrent Java network programming and Java concurrency. So that's a really good place to look. If you click here, you'll find the playlist from the last time I taught that course, and that was in the fall of 2014, starting about 8 months ago. So that's a good place to look. There's lots of stuff in here if you take a look about many Java synchronization mechanisms, much more than we talked about in these courses in the MOOCs. So reentrant locks, reader-writer locks, semaphores, condition objects, barriers, phasers, blah, 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 goes on and on and on. So that's a good place to look. I also have a series on Pearson's live lessons video tutorial site, which you can access if you are a live lessons, or sorry, a Safari book club member. And these are some really high quality professional videos, which you can watch little excerpts of some of them, that talk about all the different concurrency mechanisms in Java and show lots and lots of examples. Pretty cool stuff. I've been very happy with how this has worked out so far. So that's another good place to go if you have that, if you have access to Safari. There's also source code for all the examples here, which are available up on GitHub under my live lessons directory. And there's a whole bunch of stuff there that you might want to take a look at as well. Some of the source code that we covered from last week's Java 8 and Java 7 tutorial is also available up here as well. If you watch the video and look at the slides, you'll see the examples there. So those are good places to go to find more about concurrency than we've had time to cover in these courses. It's a vast topic. You could spend years on it and still not cover it in its entirety. Question, are there important topics that have not been covered in these MOOCs that you should study on your own? Yes, absolutely. There's many more topics that should be covered to really write production code. There's a lot of work on, obviously, software engineering. There's things on basic design patterns, which we've covered a little bit of, but could be covered in more detail. A lot of that material is also available in that digital learning link I just showed you, either through material recorded as webcasts or screencasts from my courses, or the Pearson live lessons courses. All of those are great sources to find. There's also tons of stuff on testing, software engineering, software project management, web computing, of course, which will be coming up here in the next couple of MOOCs. Security is a giant important thing. So this is just really scratching the surface. You know, keep in mind that what we're teaching here is a distillation of a small piece of what a student who's an undergrad at Vanderbilt or Maryland would cover over a 4-year curriculum. So we're just really scratching the surface of this stuff. There are many things that people need to do to go and be up and beyond. The to-dos are pretty explicit, and people will come up with similar solutions. Is there any reason to deviate from the to-dos? There's probably not a good reason to deviate from the to-dos for the purposes of the assignments, because it helps people do peer assessment. But obviously, if you were writing programs that were similar but not identical to the things that we're doing here in class, you would probably want to deviate wildly from the to-dos, because the way I've done it is not always the best way to do it. If for no other reason that you can see I keep changing my mind on a good way to do it as we go through the different material. So probably not a good thing to do for the assignment, but for anything else in real life, take what you learn here as a starting point from which you can be infinitely creative and innovative. And that's why we have mini projects. The third project is always a mini project to give students a chance to be more creative. Puts a little bit of a headache on the peer assessment process because people are seeing a lot of code they're not familiar with. And it's harder for me to give one canonical solution that looks like most of everybody else's code. But in real life, you would, of course, deviate. A lot of the things we have to do in MOOCs are driven by how easy or hard it is to assess them given the resources we have at our disposal. We still haven't really figured out how to do auto grading of concurrent programs. That's a really hard thing to do, probably infeasible in the large. So we're doing a lot of peer assessments, which is imperfect also, but at least people get feedback on their solutions and we can give some semblance of guidance. Obviously, if you're writing single-threaded code, it's a lot easier to write robust test cases that capture the bulk of the problems. Why do I give away this knowledge for free? Well, this is the stuff that we do here. I'm a teacher. I love to teach. And I actually get a tremendous amount of learning from creating this material. So as I create the material, as I do the programming assignments, as I create the lectures, I get a lot smarter. As I watch the feedback from people on the discussion forums, especially the feedback on the skeletons for the programming assignments or questions that come along, I realize gaps in my own knowledge that I have to fill to become more effective, to educate. And all the stuff that we're teaching here in the MOOC is actually pretty much identical, or as identical as ever things will be when I keep changing them all the time. They're pretty much identical to what we teach here at Vanderbilt University. So what's really cool is by creating all this material here for the MOOCs, I'm able to use that in my face-to-face courses with my students. And then as I teach my face-to-face courses with my students, then we're able to take this material and use it for the MOOCs. So there's a real great sort of feedback loop going on continually at this point, where it just gets better and better over time. And my ability to understand it and explain it hopefully is getting better too as I get more familiar with it. Let's see, another question. Under what situations will async task cause a memory leak? Does Java final thread avoid the memory leak? I'm not really sure what you're talking about. I don't really think async tasks should be leaking memory if it's used properly. If you go back and look at some of the discussions we had for assignment number 3 solution in the first POSA MOOC, the POSA concurrency MOOC, you'll see we did some pretty darn clever things to make sure that memory was cleaned up properly, even if your activity was to disappear or rotate while the async task was running. So you have to be a little careful in that type of scenario if you're using async task. Quite frankly, once you understand services well, the need for using async task is greatly mitigated. So you could still use an async task if you wanted to, but the need for using an async task is reduced quite a bit because you can do the concurrent processing in the background in a service, and then a lot of your application code becomes much simpler. And hopefully as you go through the examples, as I cover my solutions, you'll start to see that. Once you understand the patterns, you'll be much more effective at writing simpler code that's easier to verify, easier to test. Async task is sort of an activity-centric thing, and so it's subject to all the complexities of activity changes when rotations occur, when runtime configuration changes occur. Lots of things go haywire with activities, and you have to be prepared for that. But I'm not really aware of what you mean by the memory leak. There are some discussions that you can find on async tasks that talk about how you have to be careful with things like if you make an async task that is not using, it's nested inside of an activity and you don't define it as static and you don't use weak references, that's one whole issue. But that's orthogonal to async tasks. That's issues about concurrency. That's issues about nested classes. That's issues about weak references in general. So I think at this point we've covered those patterns pretty well. All the code you see, hopefully, in the skeletons is correct with respect to these issues, although every once in a while I get surprised and it comes back to bite me. So take a look at those examples. Someone wants to know what's web computing. Web computing is the topic of the next 2 MOOCs in the MOCA, Mobile Cloud Computing for Android specialization. So I will simply direct you to go and look at the web pages for the next 2 MOOCs in the MOCA specialization, and you will get an overview about web computing in that context. No sense of me trying to recreate what is masterfully described by Professor White, who is a brilliant presenter. Let's see. Oh, a good follow-up question. Download bound service async class. The onBind method is passed back as a binder object. That's correct. While the activity is sending the download callback stub, is this converted to an iBinder? Yes. So the stubs are implicitly convertible to iBinder. If you take a look at the code, you'll see how that works, because onBind returns a stub instance. So that implies, if you look down the inheritance hierarchy far enough, you'll see that a stub inherits from iBinder. In fact, I think I say that in one of the slides, that stub inherits from Android OS iBinder. So yes, that's how that works. That's described there. We'll cover that a little bit more later when we talk about patterns. Okay, well, I think we covered quite a lot of material today. I hadn't meant to go on quite this long, but that's okay. What I'll do, of course, as always, is render the videos and then upload them to the website. And at that point, you'll be able to download them and hopefully continue to learn and improve along with all the rest of us. So thanks very much. I'll see you soon.